Hi, and welcome to Area, as defined by antiderivatives and integration. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doñana Community College. Chapter 4, Integration, comes to us from Larson's 11th edition calculus text. Section 4.2 is all about area. Now, Part 1, summation and formulas. So, in order to truly appreciate what integration does for us, we need to first talk about sigma notation, where it all comes from. So the sum of n terms, a1, a2, a3, and so on, up to an, is written as a capital sigma, and then we have an index of summation. I use I frequently. We also use j, k, various, whatever. It usually starts with I equals 1 to n of a sub I. So the I here is what is changing, and it starts at 1 and moves on to n, and it's the sum. So we're adding all of these values. I is the index of summation. A sub I is the ith term of the sum. The upper and lower bounds of the summation are n and 1 respectively. So instead of writing down all of these, add, we use the summation notation. For example, if I want to add from I equals 1 to 6 the expression 3i plus 2, that'll be 3 times 1 plus 2, plus 3 times 2 plus 2, plus 3 times 3 plus 2, plus 3 times 4 plus 2, plus 3 times 5 plus 2, plus 3 times 6 plus 2. And you can see, just in typing, that was a nightmare, except for I used, copy and paste, because who wouldn't? It's much easier writing the sum using sigma notation. And when I add all these, 3 times 1 plus 2, that's 5, that's 8, that's 11, 12 plus 2 makes 14, 15 and 2 makes 17, 18 and 2 makes 20, and then I add all of these together and I get 75, and you can check that. I'm not going to do it for you. You can do this. Hit pause. And there's a question on WebAssign that's actually quite interesting, and my students, they overlook the essential part every time. So this set of students from now on, they're never going to overlook that. Notice the index of summation, I equals 4. I equals 4 to 8. I'm summing 3a. But does 3a have an I in it? No. So I don't replace anything. That's 3a when I equals 4, 3a when I equals 5, 3a when I equals 6, 3a when I equals 7, and 3a when I equals 8. That's it. I don't change anything. I don't put in a 4, 5, 6, 7, or 8 because there's no I in the expression. I'm just adding it that many times, and it turns out that that's 5 times. And 3a added to itself 5 times is 15a. So watch out for that. If the index of summation is not in the summed, the formula that I'm summing, then I don't use those values at all. True example 2 now. The sum from k equals 5 to 8 of k times k minus 4. If I were to write it out, this would be 5 times 5 minus 4 plus 6 times 6 minus 4 plus 7 times 7 minus 4 plus 8 times 8 minus 4, right? Starting with 5, ending at 8, this formula. That's 5 plus 12 plus 21 plus 32, which I seriously doubt is 770, so maybe I should count this one out for you. 32 and 21 sure looks like 53. 53 plus 12 is looking like 65. 65 plus 5 is looking like 70. So it looks like my fingers stuttered a little bit. My answer is just 70, not 770. Mistakes happen. Sorry about that. Example 3, using a new letter for my index of summation, j equals 4 to 7. If 2 over j, we're going to write it out. That's 2 over 4 plus 2 over 5 plus 2 over 6 plus 2 over 7. And absolutely I used a calculator to find that that is 319 over 210. Remember, to add fractions, we need common denominators. And I love that my calculator is a lot quicker than I am at doing that. Now let's go backwards, right? It's obviously easier to write a sum than to write out all those expressions and then figure out the arithmetic and add them together, because we all know arithmetic is the hardest part of algebra, and algebra is the hardest part of calculus. So don't let the arithmetic get you down. Let's see if we could write it in a better form. I'm given the expression 1 over 5 times 1 plus 1 over 5 times 2 plus 1 over 5 times 3, and so on, continuing the pattern, my ellipses, 1 over 5 times 11. Well, what do we have here? We have 1 over 5, and then the numbers in parentheses start at 1, and at 11 I'm adding them all. So the sum, because I'm adding them all, from I equals 1, the number that changes, to I equals 11, the upper bound, the expression 1 over 5i. Some calculators, such as the TI-89 and I believe the TI-Inspire and absolutely several HP models, you can use this notation. You could find the sum in your calculator if you could write the formula rather than having to type all of this in. And of course, we don't always need a calculator. We could do it with our brains too. But my calculator's faster than my brain. My brain's better than my calculator, but my calculator's faster. Now we're looking at the expressions. In brackets, 1 minus 1/4 squared plus 1 minus 2/4 squared plus, and so on. So I'm supposed to be able to establish a pattern from this. 1 minus 4/4 squared. So I look at what's changing. The numerators inside the parentheses of something squared is the only thing that's changing. So I keep the form 1 minus parentheses changing. I'm going to call it an I for index of summation. I over 4 all squared. And my I value starts at 1, ends at 4, and I have my notation. This notation, whether I write the index of summation next to the sigma or under the sigma, has everything to do with how much space is in my line. If it's all in a row, naturally PowerPoint, which I'm using to create these videos, puts the index next to. Whereas if it's an inline math display, or not inline math display, if it's set apart, it'll have it underneath. So don't pay too much attention to where these are. It's the exact same thing, just the display issue. I prefer them all like this. It makes more sense to me. Alright, so now I only have 2 terms, and in these 2 terms I have to figure out what stays the same and what changes. Let's see, I have 2 times 1 plus 3 over n all squared times 3 over n. Plus the pattern that has yet to be established, 2 times 1 plus 3n over n all squared times 3 over n. And I'm looking at these, and they both have a 2, they both have a parenthesis, they both have a 1 plus, they both have a denominator of n, they both have a square, they both have times 3n. The only thing that changes is the 3. So my index starts with the 3 and it ends with 3n. My numerator is the only thing that changes. Everything else stays the same, and I have my formula in sigma notation. Now here's some properties, and these make us faster than before, but still not as fast as the calculator. If I'm adding a constant n times, it's just c times n, and we saw that when we're adding 3a 5 times, we got 15a. Gauss, I believe, is the one that was responsible for this formula. Supposedly he discovered it when he was 7 or 8, I believe. I don't know, those were different days. They didn't have Nintendo to keep him distracted. So as a kid he came up with this formula. It's a great formula. The sum from I equals 1 to n of I. The sum of I squared, I cubed. Constant property, just like with limits and derivatives and integrals, antiderivatives that we saw in the last section, the constant can be factored in front of the summation, and a summation goes through sums and differences. So we have some of our standard rules that we've had for all of our new operations in this topic of calculus. So let's use the properties of summation and the Theorem 4.2 to evaluate. If I want to add from I equals 1 to 30, negative 18. Keep in mind negative 18 is just a constant. Using property 1, the formula from property 1, if I'm adding a constant 30 times, that's just 30 times the constant. Negative 18 times 30 is negative 540. So, if I want to add the summation I equals 1 to 16 of 5i minus 4, I'm going to use property 2 with the I, and property 5 with the constant, and property 6 by separating the subtraction, along with property 1. Oh my goodness, I'm using a lot of properties here. So what I'm going to do is I'm going to look at 5i minus 4 as really the sum of 5i minus the sum of 4. Here the sum of 5i, I'm going to take the 5 out. The sum of I from 1 to 16 is 16 times 16 plus 1 all over 2. Our formula was n times n plus 1 over 2. Remember, that's only when we start at 1, though. This minus the sum of a constant is the constant times the number of times we add it to itself. This is 8 times 17, right? If 16 is divided by 2, 8 times 17 times 5 minus 4 times 16 should give us a 616 as a sum. The sum from I equals 1 to 10 of I times I squared plus 1, the first thing I'm going to do is simplify my summation expression. So this will be I cubed plus I, which I turn it into a sum of sums. Sum and difference formulas. Cube formula, the sum of I cubed is n squared times n plus 1 squared all over 4. Whereas the sum of I is n times n plus 1 over 2. Complete each of these. 3025 plus 55 equals 3080. I checked this one twice to make sure it was right, so I'm pretty sure. But you should always hit pause, check my work. I do make mistakes. Alright, so the antiderivative is a measure of the area of the region between the curve and the x-axis. That's it. In order to approximate an area, we use easier shapes that we know formulas for. Now, eventually, what we want to do, I'm going to make this a little bit smaller so I can draw on here. Eventually, what we want to do is, for any function, right, antiderivative is a measure of the area between the curve and the x-axis. So I eventually want to be able to find this area. And right now we don't know very much about areas. We know a lot, but not for random curves. We know squares and triangles and circles and all sorts of things. So to find an area of a hexagon, we might break it into 6 equal triangles because the triangle formula is really easy for area. Archimedes famously approximated pi using smaller and smaller triangles to estimate the area of a circle. We're going to use a similar procedure with rectangles to approximate the area under a curve. So what we're going to do is we're going to break this into rectangles and look at the area of each rectangle. And then we're going to break it into smaller rectangles. And then even smaller rectangles, and we're going to pretend that I could draw straight lines in here. And so we're going to have what turns out to be infinitely many rectangles to estimate this area because we know the formula for rectangles. Alright, so a much better image of it, even though it does look a little fuzzy, doesn't it? If we consider the notation, the integral of f of x dx, what this is it's the summation, right? It's an elongated s. We're adding area, the height f of x times the width dx. So the width of each rectangle is our dx, the change in x. The height of each rectangle is our f of x, right, because it's hitting the line. And if I look where I have inscribed rectangles that are less than the area, and then I have circumscribed areas that are greater than the area under the curve, so the rectangles extend out, I know that the actual area is somewhere in between this underestimate and this overestimate. So we're going to look at both of those in order to find the area. If we want to use the 8 rectangles in the figure to find 2 approximations of the area of the region lying between the graph of f of x equals the square root of x all plus 1 and the x-axis between x equals 0 and x equals 2, what we're going to do is we're going to use rectangles that are from the left and from the right. So see how this rectangle hits on the right side? We might find another rectangle that hits on the left side. So I have rectangles of the same width, but now the left side. So it's a little bit under. So we're going to look at an underestimate, we're going to look at an overestimate, and calculate the results. And I totally stole this from Larson. I'm not even going to play. Let's go through the detailed explanation. So the left endpoints of the 8 intervals are 1/4 of I minus 1, where our index starts at 1 and goes to 8. We have 8 rectangles. I minus 1, I'm going to look at the left side. The width of each rectangle is 1/4. All right, I'm going from 0 to 2, and I cut it into 8 pieces from 0 to 2. Each little piece will be 1/4 wide. The height of each rectangle can be obtained by evaluating f at the endpoints. So when x is 0, so from 0 to 1/4, 1/4 to 2/4, 2/4 to 3/4, and so on in my 8 rectangles, I'm going to evaluate at the left endpoints. This is going to be a lower sum. Using my summation formulas, height and the width, I get 3.685. But I know that because I used the left side, the little black squares that I drew in, it's a little less. So I could use the right endpoints now and evaluate. And those are the rectangles that were originally drawn. They're a little bit above. It's the height of I over 4 times, f of I over 4 times 1/4. When we sum that, we get 4.038. And what we know is the actual area of the region, if I make my my rectangle small enough, is going to be between 3.685 and 4.038. That's all I know right now. So I have an upper estimate and a lower estimate, depending on which side of the rectangle I want to evaluate my function height with. So again, finding upper and lower sums for the region bounded by the graph of f of x equals x squared plus 2 and the x-axis between 0 and 3. What might that look like? X squared plus 2. I know it makes some of those words really small, but x squared plus 2 looks something like this. Let's pretend I could draw a parabola from 0 to 3. So I'm looking for this area, and we're going to pretend that I can actually hit that really well. And I'm going to break it into n subintervals. So I have no idea how many of these there are. It's n in general. I don't want to be specific. Like in the last example, we used 8. So the total distance from 0 to 3 is 3 minus 0, which is 3. And I'll break it into n subintervals. And the figure in the next slide, I'm going to show that to you. It shows several and circumscribed rectangles in this particular interval. And this is a particular number of them because we can't show n in general. We want to make these rectangles big enough that you can see what's going on. So inscribed are going to be my underestimates, and in this case, since we're looking at the increasing part of the function, those will be left endpoints as my heights. Whereas circumscribed for this increasing part of f of x equals x squared plus 2, I'm going to evaluate my heights at the right endpoints of my intervals. So left endpoints, little m sub I is 0, that's where I started, plus I minus 1, because we start I counting at 1, I want to back it up to 0, 3 over n, that's the width of my rectangles. So I find a smaller estimate, s sub n, is the sum from I equals 1 to n of f of little mi delta x. Remember our delta x? That's the width of each rectangle. Since my interval is from 0 to 3 and I cut it into n equal parts, my delta x is 3 over n. Left-hand sums, that's 3 over n times I minus 1. And when I do my sums, right, I put in my formula for f and I simplify and I use my summation formulas. And that's all algebra. I want you to hit pause. Make sure that you can follow the steps, the algebraic steps, all the way down here. Once you do, we can see that we have a lower sum of 15 minus 27 over 2n plus 9 over 2n squared. Right, if I distribute. Now, if I know an n value, suppose I cut this interval into 10 identical rectangles. I'll put 10 in for n, and I'll give you an approximation for my sum. Suppose instead I want to cut the interval from 0 to 3 into 100 rectangles. My n values, I'd use 100, and I'd find the sum. But that's a lower sum. All right? If I'm using right endpoints, and I can't believe I found another error, that should be a capital S of n. Only the second error I think I found in this book, and I believe this was from WebAssign, so who can we really fault there? The sum from I equals 1 to n of f of capital M delta x. Still, the same ideas. Make sure you follow the algebra, make sure you see what's going on. And notice these values are very similar to what I had before. As n gets large, think about limits. As n goes to infinity, these are going to become 0. This area happens to be 15. With the lower sums, we had 15 minus 27 over 2n plus n over 2n squared. Upper sums, we have 15 plus 27 over 2n plus n over 2n squared. Either way, we have an upper sum, and on the previous slide, we have a lower sum. And for a specific n, we can find the value. And in general, this is a great approximation. If I cut it into 2 rectangles, 1 rectangle, a million rectangles, whatever it is, we can estimate the area. Alright, so now we want to find the region bounded by the graph of f of x equals x squared plus 3, the x-axis, and the vertical lines x equals 0 and x equals 1 as shown in the figure. Oh boy, how are we going to do this one? So when we're looking at our function, f of x equals x squared plus 3, and I want to cut the interval from 0 to 1 into n subintervals, well, the total length of that interval is 1, divided by n, so the width of each rectangle is 1 over n. I know my height is f of x, which is x squared plus 3, and I could choose any right endpoint, left endpoint thing I want. In order to find the area, what I'm going to do with either the lower sums or the upper sums, I'm going to let n approach infinity for my sum. So the limit as n approaches infinity, the sum from I equals 1 to n of the area of the rectangles, right? Height f with the delta x, with delta x equals 1 over n. Here's my f of x, my right endpoint, so my ci values are 1 over n, I over n, as I goes from 1 to n. I can use my formulas. This 1 over n has absolutely nothing to do with the I, so I can factor it out. Formulas. I'm still finding the limit as n approaches infinity. Keep in mind this goes to 0, this goes to 0. 3 plus 1/3 gives me an area of the region of 10/3. This is exactly what we do with antiderivatives or integrals, definite integrals. All it is, the limit as n approaches infinity of an infinite sum, that's the elongated s we have in integration. The area, the dx that we have in integration, that comes from our delta x. It's the width of a rectangle. The function, the integrand itself, that's the height of the function. So I have a height times a width. I'm summing up infinitesimal rectangles in order to find this area. To me, that's one of the great things about math, is we could do arithmetic with infinity. I guess this is not arithmetic, but we could do some work with infinity and get a real number answer, something that will apply to all kinds of majors when we're finding these answers. So thanks for listening. Area, where it comes from, how we got the integral. Feel free to hit pause, go back. That's why I do these videos a lot of times in class. I get questions, I go off on tangents, but here you can stay focused. Thanks for listening.